The analysis of individual functions by looking at its derivative and second derivative is helpful, but it can be very repetitive, especially when we're looking at at functions that are related to one another. And that idea of functions that are related or somehow similar is given the name families of functions. These are all families that have things in common, just like a family tree, but where individual members of this set of functions are distinct in some way. So typically, these families have one or more parameters or constants in them. These are constants that aren't set up front. Let's take a look at an example and see how it works. This function here, f of x equals a to the x over x squared plus b, is a related set of functions. They all have something in common. It's always an x in the numerator and x squared plus something constant in the denominator. But we don't know up front what a and b are going to be. Then the question becomes, well, these graphs will all look similar. What will they have in common, and what will they have as differences? Let's take an example. We have two parameters here, a and b. One of the simplest ways to get started on a question like this is to get rid of one of them, to pick a value for one and just see what changing this value does if b stays constant. All right. If b is equal to 1, then our function simplifies down to ax over x squared plus 1. And we can think of that as a times x over x squared plus 1. But that is exactly the graph from the previous example. And the a, if it's a constant outside of all this, is simply a vertical scaling. So, knowing the graph of this function, which we analyze using first and second derivative information, we can get a sketch of this family of functions where we multiply by some constant out front. So we can generate some sketches fairly easily with that. We'll have the same reference points, -1, negative root 3, +1, positive root 3. And we had our canonical graph here, concavity changed at -3, slope changed at -1, slope changed at 1, and then concavity changed at root 3 there. This was the graph of f of x equals ax over x squared plus 1 if a equals 1. If a were to equal 2, that would be a vertical stretch where all the points on the graph are magnified in the vertical direction. But all the analysis of the critical points would stay the same. The concavity would change, the slope would equal 0 at the same point as before. So everything is simply magnified vertically. This graph would correspond to this function with the parameter, or the a value of 2. And another option we might consider is, what if it was half as big? What if a was a half? Again, we'd have a vertical compression, a vertical change, in this case a vertical compression, by a factor of 2, or all the heights would be 1/2 of what they would have been for the original function. So that's how we can see the family of functions. These are all related. They all share common features like this root and the x location of the critical points, but they're all a little different in their vertical stretch and vertical height in general. All right, let's go back now and say, what if a were 1? Again, we have two parameters. We're trying to explore what's happening here. If a is equal to 1, then our function can be rewritten as x over x squared plus b. What does that change? Well, let's talk about the first derivative, because that is not a standard transformation. Changing this denominator plus term here does not do a horizontal shift or vertical shift. It does something different. Let's see how it plays out. Our derivative would be 1, so quotient rule, derivative of the top is 1 times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. Now if we simplify that one step further, we'll have x squared minus 2x squared. So the b will stay the same, but we'll have minus x squared over x squared plus b all squared. And we can factor that as root b minus x, root b plus x. We have a difference of squares, but we have to consider what the root of b would be as the root of the first term. And what does that lead us to? Well, this is very similar to our earlier example. And there what we found was 0 was a reference point, and we had 1 and negative 1, but now it's going to be negative root b and root b. We're going to find the signs of the derivative. Oops, pardon me. We're going to find the signs of the derivative are exactly the same as we found in our simpler function, the x over x squared plus 1. They're going to be positive in this range, negative here, and negative here. The only thing that's changing is the location of the critical point. And actually, we can find that explicitly. The critical point, we have the sign of f prime going negative, so the graph is going down. This is f. Going down, hitting 0 slope, then going up. There's going to be a critical point at that transition. That's going to be a local minimum, and then increasing to a local maximum, back down. The location of the critical point is going to be at x equals negative root b, would be the first one, and at x equals root b. The matching y-coordinate at that point we can find by plugging into our function, simplified by a equals 1 here. We're going to have the y-coordinate, or the f value, being negative root b over x squared plus, pardon me, b stays the same. We're plugging in x for all the x coordinates. Negative root b squared plus b. That's going to be negative root b over, well, that's b plus b, that's 2b. So if I want to know not just left to right where this critical point is, but vertically where it is, we now know what the y-coordinate is. Likewise, the critical point at the peak of the function is going to occur at positive root b, so we're subbing root b for x in here, divided by root b squared plus b, that'll be root b over 2. So we've analyzed this scenario with the simplification that a will be 1, and what we found is we're still going to get the same basic up and down shape as we found in the previous graph. Going back a step, we're going to have the same shape, but changing this term in the denominator is going to move the location xy's of the critical point, and it's also going to change the y-coordinate of it as well. Here's the y-coordinate, and if we change b, we're going to get the height also being scaled as b changes. So let's see how that works out. We'll sketch our graph, and let's do a few different positive values of b here. Let's say b equals 1. That's our nice easy one. And what did that give us? It gave us the critical points at x equals negative root 1 and positive root 1, and the y-coordinates there were going to be negative root 1 over, let's slide this down here. The y-coordinates to match would be at negative root 1 over 2 times 1 and root 1 over 2 times 1. Okay, so if we get those values and we can actually put them on our graph now, let's go to 1 and negative 1. This graph here, we can actually be precise about the y-coordinates now. We weren't really before. They're going to be at 1/2. So this is 1, that's 1/2. The other one will be at negative 1/2. We can sketch out the graph like so. That is the graph we would get if a were 1, so this is also all subject to a equals 1. but if the b value were also equal to 1. Let's try if b equals 2. We would get the critical points at x equals negative root 2, y equals, we'll keep the same pattern as here, negative root 2 and positive root 2, and the matching y coordinates would be at negative root 2 over 2 times 2. And the other y coordinate would be at positive root 2 over 2 times 2. Just going back, I'm getting this y coordinate from root b over 2b. That's what I'm missing there. Root b over 2b, negative root b over 2b. There's our b, root b over 2 times b. And so that, we can calculate it out. Root 2 is about 1.4, so about here. Let's do this one in, we'll do this one in green. So here's root 2, here's negative root 2. The y coordinate would be negative root 2 over 4. It's actually pretty small. It's actually smaller than a half. So it'll actually be lower. And likewise down here it'll be lower. So by having that larger b value, the peak that we reach happens later and is less significant in height. There we go. Be something like that. Let's clean that up just a little bit further. So in fact, these family members can cross, and I think they will in this case because of the flat slope and the change in concavity. When that's going to happen is going to be different here. So it'll go up, it'll hit its maximum at x equals root 2 and then keep going. This would be b equals 2. And we could also pick a smaller b value, like a half. Won't go through the full analysis here, but it'll happen at 1 over root 2, which is about 0.7, and it'll be a bit higher. So we'd get a graph that would be shaped like this, and higher as well. Likely something like that. Again, we call this a family of functions because the functions all have shared common features, the roots, the up, the down shape, but they all are individuals in where they actually have their critical points, their maximums and minimums on this. So far we've only explored this family when the values of a and b were positive, and that's a reasonable collection to assume. If a were negative, what would happen though? Well, a is just a multiplier of the whole function. It can be factored out. And so a negative would give us a vertical flip of the graph. And if that's the case, the basic shape would be the same, except instead of being down like this and then back, the graph would be like this. This would be with a negative. Now the b being negative starts getting trickier because then we can have divide by zeros. So if b is negative and, if b is negative, x squared minus something, then we can have zero denominators. That was never a problem before. And so the functions will look substantially different. And if that's the case, if you think of a family tree, b being negative would be a whole other family from the other ones, or a very different branch of the family. It wouldn't have the same up and down shape because we start getting vertical asymptotes and a whole collection of other behaviors. So typically we'd say that our family of interest that all has this basic shape would be all a values and b positive only. That family all shares resemblances. If we let b be negative, we start getting into scarier territory, or very different territory where we can't say there's as much of a resemblance anymore. Last but not least, if we think of a design question, if we want to design a function that has the same basic shape, but it has its particular peak at 110, how would we go about finding that particular member of this family? So now we're looking for, we've got a suspect in mind, and we want to identify the family member that shares this particular characteristic, that it has its peak at x equals 1 and f of x equals 10. Well, we said before that the critical point, x coordinate, is going to be given by square root of b, or minus root b here too. And that means that if the critical point is at x equals 1, that means that 1 is equal to root b, or b is equal to 1. That's the family member we're going to be looking for. The next question would be, what's the a value? So we know one member, one parameter value. How would we make the peak occur at y equals 10? Well, we know that from our earlier analysis that if ax, well, actually we can just plug it in. We don't have to overcomplicate this at all. We want to use the fact that f of 1 equals 10 to find what a will be. So we'll have 10 equals a times x. Well, we're interested in the y coordinate just at x equals 1. And we said that b was also equal to 1, so that'll be 1. So we'll have 10 equals a over 2, or a equals 20. So this graph, the one we're looking for, the member of this family of functions, starting with that as our canonical form, would be 20x over x squared plus 1. A equals 20, b equals 1. So we note that it's a fair amount of work to analyze a family of functions like this, but once we've done the analysis and we want to find members of the family that have particular characteristics, and this is very common, find the best fit line, it's very straightforward to do so once we have these relationships between the family members identified.